So we have Miguel Preto from the ARI, and he's going to talk about something which we have seen today in the morning. We'll say a couple of things, or more than a couple of things about this. On strong mass segregation around supermassive black holes or massive black holes. And well, by the way, Tal is still alive. He arrived, and he's on the way to the institute.
All right. Yeah, thanks. Okay, so this is this work on mass segregation is work that I'm doing in collaboration with Pau. Yeah. Okay, so just to introduce the problem, although Clovis already made an introduction this morning. So basically, what we're dealing with is we're studying the stellar distribution in the central regions of the galaxy, in the central 1 to 10 parsec. And this is a region, of course, as you know, of very high densities and relaxation times, which are interestingly smaller than the double time. So relaxation effects play a role. This means that one of the ways of approaching to this type of problems is using the Fokker-Planck equation. Another way, and this entails a lot of assumptions, and I'm going to summarize in a few slides. N-body calculations, on the other hand, do not make all those assumptions. So they are basically, we have Newton's equations of motion, and that's it. The price to pay is that you need a very large number of particles to avoid to have, due to the graininess of the system, to avoid to have spurious dissipation. So you need to have a large n in your calculations, and as a result, calculations are very long, take a very long time. And this means you need special hardware, and means that the results take a long time to appear. I'll talk later about this and also talk about the limitations of current algorithms. I'll mention the limitation of current algorithms for n-body simulations and point to the discussion we're going to have tomorrow afternoon about future developments and improvement to do n-body calculations for this problem. Now this is just a cartoon or very schematic picture of what happens with galaxies with massive black holes in their centers. So imagine that time goes from up to down in this direction. And so in the beginning you have, let's say, isolated galactic nuclei with a central massive black hole in the center. And due to this evolution of collisional system, you have a growth of density curves, and MRIs might result. Afterwards, you might have mergers, and in the merger of galaxies, the binary black hole system interacts with the field of stars around it, and ejects many stars. This leads to a decay of the density curve, and then to future merger and spiral merger of the black holes eventually. And then after that, you are getting this situation of isolated galaxies where density curves might grow again, and also massive black hole might wander because it might take, due to the after they merge, it might be ejected from the center, depending on. Might be ejected from the center, and then it might wander and might take a long time until it settles down in a competition with the rest of the stellar system. Again, MRIs are possible sources of gravitational waves. So here in this picture, you just see that. I just wanted to point out now also as an aside that actually this problem of isolated massive black holes in the center of galaxies is actually numerically more difficult to deal with than the binary black hole problem, because as you see, the densities tend to be very high, and you have to integrate for a very long time very eccentric Kepler orbits. And so this is, well, these are difficult to do. So this is also what we're talking about is the collisional. There is this kind of dichotomy between lattice nuclei that might be collisional or collisionless. Of course, for the systems of interest for LISA, which are massive black holes of that are not so massive, but 10 to the 5 to 7 or so, we are in this regime where the age of the system is actually larger than the local relaxation time. And so it means that the stars will diffuse in phase space and erase memory from initial conditions. And so they tend to evolve towards a kind of universal steady-state solution, which are the type of power laws, Bakalov power law solutions that Claudius was talking about. This is in contrast with systems where you have much more massive, supermassive black holes, where the relaxation times are much larger. And those still preserve, but those are those of interest for us. And so, although there are not many, this is an estimate from American Cell estimates of relaxation times at influence radius against the sigma velocity dispersion, and of course, this is we're interested in the systems that are down here with smaller relaxation times, smaller than the Hubble time, and there are not many observed, but we expect that there exist many, of course, from general articles and areas. Okay, so I'll just ask you to make a kind of summarizing what are the differences between Fokker-Planck, what are assumptions of Fokker-Planck approach, and differences that they have with n-body. So I list them here. Some of them I don't think are very important, and the ones that are in bold are the ones I think might be important. I just go through the list, and I stated first, scattering. The assumption of Fokker-Planck approach is that you have small deflections. So at each encounter between two stars, you have velocity changes by a small fraction of the velocity of the stars themselves. And they are uncorrelated as well. So they are uncorrelated. So basically you neglect all large deflections, all close encounters that might lead to ejections of stars from the cusp, and so on. This is potentially an important factor that we neglect in Fokker-Planck. Then there are a number of other less important, I think, local approximation, which means that at each encounter we assume that the star is kicked in velocity but maintains its position, and also the orbital averaging of diffusion coefficients. I mean, probably these are not very serious limitations, but then you are limited essentially to spherical symmetry and also to a black hole which is fixed at the origin. This, depending on the problems, might be an issue or not. Let's say spherical symmetry. I mean, if you're thinking about the systems that Claudius was talking this morning, I think this is not a problem because you are very deep in the cusp. And so the potential is limited by the black hole. It's spherical symmetry is probably a good assumption. But let's say if you want to think about these other sources for memories, like the binaries which are tidally disrupted, they might come from much farther out, at places where triaxiality, even if small effect of triaxiality, might affect the orbit of these binaries. And then you want to treat it in the spherical symmetry, for example. And the black hole fixed, as well as I said, there is no one has ever been able to figure out a way of doing the Fokker-Planck calculation, as far as I know, without assuming that the black hole is fixed at the origin. And if the black hole takes a long time to come back to the center, after it being ejected, after a merger of a binary or something, then you really want to be able to compute, don't use this assumption. So this, I think, is also an important limitation of Fokker-Planck. Then binaries and triple systems are order encounters are neglected. Fokker-Planck is not time reversible. You have to put by hand, like assumption that encounters are uncorrelated, and Newton's equations are time reversible. I think also it's not a big deal, but it's a difference, and it's an assumption. And okay, then this is the form of the Fokker-Planck equation in energy space, as Thomas was talking. So this is basically a particle number conservation in energy space. And there is a flux here, which is given by R, which is given by these are diffusion coefficients, and the function f, which is the number of stars per unit like this here, number per unit volume in phase space, which relates to the number of stars in energy space with this expression. So this is basically a conservation of particle number. And the boundary conditions are here done by, you need to impose some constant value somehow, because there's a reservoir of stars outside at some outer radius. And you have to set it to 0. I mean, you don't need, you might choose flux, different ways of putting the boundary conditions, but these ones are motivated in the sense that you expect that the star, some energy will be disrupted by the black hole. Here we neglect Boston effects because you don't take into account the dependence on angular momentum. And this is just...
Can I ask you something?
Yes.
So you've described the situations in which you don't expect Fokker-Planck to work well. But in situations where you do expect Fokker-Planck to work well, for example, in the process of mass segregation.
Is there a microphone?
I was saying that Miguel has described situations in which he doesn't expect Fokker-Planck to work well. But my question is, in situations where Fokker-Planck is expected to work well, for example, in the problem of mass segregation and galactic nuclei, do you get sort of the same results from Fokker-Planck from n-body simulation?
That's what I'm going to show.
What is the answer?
Well, they are pretty close. They are pretty close. But the problem is that this is not the end of the story, because you want to put other things into your study. You want to study well, it's difficult to put extra physics in the Fokker-Planck equation. Like, you want to treat stellar collisions. If you really want to be very precise, we didn't reach this point in our n-body simulations yet. But if you want to be very precise in the study, you have to take into account, for example, stellar collisions.
Why is it hard to include?
You can put in Fokker-Planck, but I mean it's just an ad hoc sinc term that you put in the equations. Then it's also the same thing. It's difficult, let's say, resonance relaxation. You can also put a sinc term there to model, but you need. But I mean, it's not really. You have to calibrate with n-body simulations. Otherwise, you don't know how to specify the sinc term accurately. And if you want to study, for example, what are the rates for MRIs, I think, and you want to know, I mean, you want to compute things at a small number events, then I think you also...
Surely not going to do it using n-body simulations, the MRIs.
Sorry?
Surely you can't do MRIs using n-body simulations.
Not at this moment. No. It's quite difficult. Yeah.
I would say you can use n-body simulations to calibrate from Planck simulations to use them.
Yes. Okay. So here you have the. So I just rewrote the Fokker-Planck equation. You have your diffusion coefficients, which depend on f. So it's a nonlinear equation. And then you get to the question of what's the steady state, the solution of the Fokker-Planck equation. And the steady state, this was the hypothesis done by Bacall and Wolf, which was that, let's suppose that within a certain region where the potential dominates, the potential of black hole dominates the dynamics, you assume that, that these power laws are the solutions. And then you can extract these exponents for the power laws just by looking at the flux terms of the Fokker-Planck equation. So basically, you say, okay, I have a flux in the energy space, and if the boundary condition in the inner boundary condition goes to zero at infinite energy, or R equals zero, then the flux goes to zero, because the flux is roughly done by this, and this scales with R in such a way that goes to zero at infinity. And so you get a zero flux solution where you have equal number of stars drifting in and out. But on the other hand, but of course, in a real system, you need to have an inner boundary condition which is not in infinity, set for a given finite energy. And in this case, you can, what you see numerically is that you have a so-called neural zero flux solution, where the flux is almost zero, and you have a very close P1/4 solution. And you can see these are Fokker-Planck calculations. So you see on the right hand side plots are just a distribution function evolution. So they start. This is the initial condition, which corresponds to a spherical galaxy model with a shallow inner density cusp, and and you see that there is a growth over relaxation time and convergence to a 1/4 solution. F proportional to 1/4. These are just two different cases for two different fractions of molecular mass. So it's 1% of they are quite heavy in this case. 1% of the cluster. This is 5%.
Miguel, what is this 1%?
Huh? Sorry.
I didn't hear what you were saying. What is this 1%?
The one. This 1% is the mass of black hole is 1% of the total mass of the model. That's what you're asking. This was done actually. These numbers were chosen. They are a bit on the high side. Were chosen then to compare things with the n-body populations. That's the reason. And so you see that they develop. Of course, they overshoot a little bit here because they have to obey the boundary condition, which in this case was at E equals 1,000. And this is in density, a special density, where you start, so as I said, a shallow inner cusp, and which starts in dynamical equilibrium, and then you see the growth of the cusp towards the single solution. So this is for single components. And now you need then to make a comparison with the Fokker-Planck, and then this is shown here. So of course you distinguish different curves. So very noisy is n-body, smooth is Fokker-Planck, and these are kind of instead of calling this Lagrangian gradient, I would call this Eulerian radius. So it's on this axis I have the mass inside a tenth of the influence radius of the black hole, and against time, evolution in time, in units of relaxation time. So what you see is you can choose just one of these curves and choose this one. You see that at this radius the density starts to increase. So there is the collapse and increasing the density slope, and you get to a point, you get to a maximum, and then afterwards you just the cluster just continues to slightly and slowly re-expanding due to the fact that started building start the other ones, conservation of energy to go out. And this is the n-body realization of the growth of the density cusp. This was done just for 3 different black hole masses, which I don't remember exactly the values. But here, these 2 arrows point. This is the influence radius of the black hole in this model, and this is the 10th or 10 or 20% of the, I think it's 10% of the influence radius. So you see that it's roughly at 10% of the influence radius of the black hole that the asymptotic density curve is created. And outside is still not getting there. And this is the very noisy realization and extracting the Fisher function from the n-body, which is quite difficult to get. And just this is the model we are using. These are the range of particle numbers that are, which are not at this moment feasible to do these calculations, direct n-body calculations. Now, black hole scaling relations. Okay, now you can write, so here you can write the equations. So you have one index I for each component, and you can write them down. I mean, you can write this in general for n components. Let's think about only two. And you can write expressions for the fluxes. And you can do another hypothesis. You again assume that if of the components the solution of the equation obeys this power law, and if both fluxes go to zero in steady state, then you can work them out that you get this relation between the slopes of the components. They go with the mass ratio of the system. Now, nothing in this actually, in this derivation implies, so basically it means that you have the largest slope is for heavier particles, and then you have the lighter particles have this relate to the heavier ones to this ratio. But no, never here is derived the value 7 quarters actually. So I mean, the heavy component is not shown. I don't know. I think they don't show in the record. That should be 7 quarters if you have one component. And of course, you can argue physically that if the heavies, let's say, dominate the potential, then they should more or less evolve almost in isolation. It should converge to 7 quarters. But okay, and these are 3 examples of n-body simulations with 2 components. It's the work that me and Pau are having preparation. And so here you have on the left side you have the light components, the density curve of the light components, and on the right side you have the heavy components. And you have here the parameters we have chosen for the run. So basically here you have that the massive black hole, the black hole was 1% of the total mass of the cluster. Here it was 5%, here it was 5%. This is just the number fraction of the heavies. So they are quite high here, so half, 0.1, 0.1, and this is the mass ratio, heavies and lights. And actually, I wrote here that if I adopt the delta parameter by Clovis and Tau, these are the numbers that we have. So they are all of those are above 1, which is kind of the dividing line in their plot. And you see that roughly the density curve is not much. It's very close to 7 quarters for the heavies. And of course, these are all very noisy. And for the lights, once you're inside the 0.1 influence radius, you get very close to the 1.5 slope. So these are very close to what black hole scaling relations predict. These, by the way, so these calculations are done with 128,000 particles, all of them, I think. Now, this is just a detail of the stellar cusp is not in equal partition, and we can see that from the simulations, but I just skip this. And okay, now we get into the... So this is the plot that Clovis was showing. This is the delta parameter, which is proportional to this quantity. This is the average value of the cusps. Not for the spatial density Rho, but for phase space density F. And this is, okay, to the right is really the region where Bacall-Wolff solution is supposed to apply. And to the left, to this line, it's the region of strong mass segregation, where you see that the slopes are really increasing. Of course, as you get to the higher lower to left and to the left, you get to very realistic from astrophysical point of view.
So it should be the other way around, and H over NL?
Sorry, can you?
Should be the other way around, and H over NL?
I guess you're right. Yes, it is. It is NH over NL. Sorry. Okay. On this, I mean, this is things that we are really getting. We are not getting results, so this plot is still a bit not very blurred. Sorry, but these are calculations also from Frocken-Planck. These smooth lines, where the colors were chosen to compare, just to have the same values as this one is on plot and tau plot. So this is the red line is for the mass ratio of 10, and the green line is for the mass ratio of 3, which are corresponding the same colors to this plot, of course. And these points here with the corresponding colors are the n-body very quickly and roughly then estimate of the density slopes. So we are, I mean, actually, I didn't include the slopes from other simulations we have. I could have done. They are very close to this result for delta big larger than 1. But
Miguel, sorry to interrupt you, but is this the delta you used, or is it the delta that Pau and I used?
No, it's a delta. No, this was a typo. This was the
another factor.
Yeah, with another factor. Yes. 4 over 3 plus.
But with another factor that's on the mass ratio.
Yes. I mean, the results are qualitatively they are very similar. So we have this regime of mass segregation, and the n-body simulations in case, for example, the R equals 3 are very close to the curve. Think of Frocken curve. Take into account that, I mean, this is very noisy so the slopes, the estimate of the slopes is, I mean, it's not. So the n-body realization is quite noisy, and these are just the first estimates that we're having for the density slopes. But so what I want to say is that qualitatively we're getting this effect where the n-body simulations slopes measured from the n-body simulation are quite high and agree with this strong mass segregation regime. Yeah.
Two related questions. One is how do you determine whether you have reached steady state? And the second one is if you have succeeded in determining that, how long does it take to reach steady state?
Oh, these things happen well in the fraction of relaxation time.
How do you define relaxation?
Okay, define relaxation time as the radius where the first influence at the influence radius first. And influence radius is the radius where twice of mass of black hole is inside, the closest to us.
This is the combined relaxation time of the lights and the entities, or the dynamic function?
No, this is the dynamical the relaxation time of the lights.
Due to the lights.
Due to the lights. So if it were only one component, it would be only one component, basically.
Okay.
Actually, it's not. Actually, yeah. And this happens. So the steady state is reached roughly at a fraction of this value. Can be. I mean, it varies 0.2, 0.3, depends. Depends actually. I think it's roughly over relaxation time over the mass ratio, roughly.
And that's the time to reach steady state
No, for the areas, for the areas. Light state only, yeah. And you can see whether they reach steady state by looking at that evolution of the mass inside. So as I showed you before. Yeah. Yes. Okay. So here, this is the point where the cusp has grown, and here you reach more or less the steady state and just re-expand. And you see that here, even for a single component, is on this definition of the relaxation time, the steady state is reached at, let's say, 0.5, 0.6 of relaxation time. Of course, it can depend depending on the defined relaxation time.
So you say that it's the relaxation time due to the rise divided by the mass pressure. So that's the friction.
Yeah. So, yeah.
And the light reaches steady state in the relaxation time.
I think so, but in several of the calculations, actually, they haven't reached yet. There are some running calculations that they haven't reached, so I have to check. But yes, that's the trend, I think. Where was I? Okay. This is an example. Just of one realization like this, where delta is 0.25. Mass pressure is 3, and you see here the curves. This is analytical initial curves, and these are the light and heavy components. And actually, yeah, they cross over here, which is roughly 100 times smaller than the influence radius, roughly. Of course, to make really precise statements, I have to average over many realizations because, this is all very noisy. I cannot believe the exact point where this is crossing. It has to be the real thing.
But if you determine the steady state by the amount of mass within the radius of influence, you define the range of influence to be the radius where the amount of mass is twice the length.
No. Okay. In all statements I think that I make about the radius of influence, they always refer to the initial model. Okay, it's not evolved with time. So it's a reference radius at the beginning of the model. And then I was looking actually not at looking at this evolution at the influence radius. I was looking, for example, in the case that I showed, at 1/10 of the influence radius, because that's roughly at that radius that the asymptotic slopes are reached. And here I just had, I didn't have time to correct this. Some calculations that I have, but I didn't have time to analyze yet. About with a continuous distribution of mass. This should be proportional here. And this is the power law minus alpha. It's the number of stars with mass m. And there are several cases here which are basically, I have some cases with alpha 0.1, 0.3, 1.3, 2.3, just to test numerically the different evolutions. And what I find promising in these results is that this is the total. I didn't have time to look at to decompose the several mass ranges, but total density is very close to 7 quarters. And people usually assumed that it should be made 1.5. And maybe this is a link of strong mass aggregation also in a continuous distribution of masses. But this has to be still confirmed further analysis. But they are fairly steep, the cusps. And just to finish, just want to make a connection with what me and Pau are going to talk tomorrow in discussion. Which is, now we are able with the current hardware to treat and recover the global bulk properties of the stellar system. But now if you want to study things like the Wolfscone effect, which are very, very, very fine effects in phase space, you have to really push to a very larger dynamical range, larger than we are getting right now. And we need to treat and study many very eccentric, weakly perturbed Kepler orbits, and also lattice effect and so on. And you need to preserve a very complete phase space structure if you want to study resonant relaxation, or if you want to study the possible instability that Scott Tremaine has pointed out, that if you have a system with an empty loss column, M equals 1 mode might develop in a cellular distribution. And to study that, you need really very accurate integrators and very great methods. And so, I mean, it's something that we're going to discuss tomorrow. Not only do we need different integrators, is there a chance that we can use a sympathetic integrator that is efficient for this type of problems and put it in the n-body plate? That's something that we are thinking about, and we're talking about that tomorrow. So as a summary, okay, there is a very good agreement between photovoltaic and body. Mass segregation is very significant and accelerates the evolution. And there are these two branches, as Alexander Oldman has proposed. We think we can confirm that qualitatively from n-body simulations as well as from Fokker-Planck as well. Fokker-Planck we already have. So we expect a very strong possibility of cellular black holes in the central regions, and of course, you know about that, maybe a large pool of candidates for MBHs. Okay, thank you.
Any questions?
I'd like to point out that the last conclusion is actually.
Hi, Tal.
Hello.
Yeah, okay.
I've made it surprising. So the last conclusion is actually, I think at this point, is something that we can hope for, but it's not clear at all, because there is this, if you want, not a paradox, but something counterintuitive, that in fact systems that overall have less stellar black holes in the general population tend to take those fewer black holes and concentrate them more in the center. Now, whether or not when you compare two systems, one which has many black holes and therefore never reaches the strong segregation solution, with another one which has a fewer black holes in general, but then it concentrates them more. The question is, which one will at the end of the day have more stellar black holes, say in the radius where they can actually become angry? And that's I still don't know the answer to that. So I think that's something that has to be tested.
Well, a partial answer to that is maybe there is this paper by what we talked about this morning, by Larry and Dave, where they show two density plots, one with a number of black holes like usually suits, so 1 in 1,000, and one with 1 in 100 stars to be black hole. And so the reason, and if you look at the distance of say 100 parsec, then the ratio between these two simulations is not 10, but it's still that the one where you have more black holes outside beats the one.
So strong segregation actually would be an effect that
So it's
at the end of the day would give less enemies. I mean, situations which lead to strong segregation
have less enemies.
Less enemies.
But you can. Yeah, so the strong segregation makes the difference between these two situations less, but not doesn't.
Yeah, but then there are issues like resonant relaxation, which actually cares about the mean mass and not the total number. I think it's actually an open question.
Any questions, comments? If not, thanks again. I'll see you tomorrow.